So section 8.1 is the last section that we have in our course. So that's exciting. We're almost done. 8.1 is about sequences. And just if you ask, a random person, hey, what is a sequence? They would probably say that it's a pattern. And that's exactly what we're dealing with, okay? Now we're going to give it a little bit more vocabulary, a little bit more context than that. But you can think of a sequence as basically a pattern, okay? Just the set of regular integers or regular whole numbers is a sequence. 1, 2, 3, 4, 5. That's a sequence or a pattern of just counting by ones, okay? Now we're going to get a little bit fancier than that. And we are going to say that our domain is the set of positive integers, like 1, 2, 3, and that the individual terms in the sequence are would be like our y values. So if I had my x's and y's, and let's say that my formula was, y equals 2x plus 3 or something like that. This would be a function. We're used to kind of thinking of this as a function. It's a set of ordered pairs. You could graph it. It passes the vertical line test, okay? Well, a sequence is the same thing, only your x's are going to be your domain. Your x's, which are the domain, are going to be the term number of your sequence. So in other words, if I wanted the first term, the second term, the third term, the fourth term, etc., I could plug in a 1 into this formula. So 2 times 1 is 2, plus 3 is 5. 2 times 2 is 4, plus 3 is 7. 2 times 3 is 6, plus 3 is 9. 2 times 4 is 8, plus 3 is 11. So this is kind of how we've been working with functions this whole time. When we start talking about a sequence, we're going to, instead of x, we're going to call those n's. We're going to replace it with n. And we're going to think of n as our term number. And instead of y, we're going to call it a sub n. In other words, a sub whatever term you're talking about. A subscript that number. So a sub 1 would be the value of the first number in my sequence, which would be 5. A sub 2 will be the value of the second term in my sequence, 7. A sub 3 will be the value of the third term in my sequence, 9. And a sub 4 will be the value of the fourth term in my sequence, 11. So basically you might see the numbers, 5, 7, 9, 11, 13, etc. And you would know, oh, a sub 1, that's the value of the first term. A sub 2, that's the value of the second term. Now, you do have to count by ones here, and you can't have like a 2.5. Now, normally in a function, I could plug in 2.5 in for x and see what came out for y. Can't do that with sequences, okay? You got to start with 1 and you got to plug in whole numbers, okay? But a sequence is a function whose domain or x values is the set of positive integers. So 1, 2, 3, 4, etc. The terms are represented by a sub 1, a sub 2, a sub 3, a sub 4. The nth term or a general term can be found with a sub n. So we use a sub n to say, hey, what's the formula of the terms in this sequence? And our formula would be 2n plus 3. That's our way of saying, okay, multiply your term number by 2 and then add 3. And that's exactly what we did. To get the first term, we plugged in 1 for n. 2 times 1 is 2, plus 3 was 5. That's why 5 was the value of our first term. Now notice it's nice to have this general term or nth term formula because they could say, hey, find a sub 7. In other words, find the 7th number in the sequence. So you could say, okay, well, that's going to be 2 times 7 plus 3. 2 times 7 is 14, plus 3 is 17. So even though I didn't find the 5th, the 6th, etc., if I kept this sequence going, the value of the 7th term would be 17. Okay? All right, so let's take this sequence right here. This 5, 9, 13, 17, 21, ... meaning the pattern keeps going. And they want to know what is a sub n. In other words, what is the formula for the nth term in this sequence? What's our formula? What's our process for finding any term in that sequence? So if we continued on in Chapter 8, which we're not, we're stopping at 8.1, but if we continued on into 8.2 and 8.3 and kept working, we would learn some little shortcuts of different types of sequences, such as arithmetic or geometric and so on. But one little trick that I like to do, like to start with when I'm trying to find my general term, my formula for the nth term, is to say, okay, can I tell if they're adding the same thing or multiplying the same thing every time? And in this case, to get from 5 to 9, we would add 4. So I wonder if they're adding 4 every time. Well, to get from 9 to 13, they would add 4. From 13 to 17, they would add 4. From 17 to 21, they would add 4. So I seem to notice kind of what's happening here. They're adding 4 every time. So what I've noticed from experience here is that I'm going to say 4n. Since they're adding 4 every time, I'm going to say 4n is part of my sequence. And let me check it. If I wanted the first term, I would plug in 1. Well, 4 times 1 is 4, but I'm supposed to get a 5. I'm off by 1. If I wanted the second term, 4 times 2 is 8. But my second term was supposed to be 9. I'm off by 1. If I wanted the third term, 4 times 3 is 12, but my third term was supposed to be 13. I'm off by 1. So what I learned is if they're adding the same thing every time, just multiply that number by n and see how much you're off by as you check. I was always off by 1, so I bet I could add 1 and it would work. So the value of the first term, if I did 4 times 1 plus 1, 4 times 1 is 4, plus 1 is 5. That seems to work. What about the second term? Well, 4 times 2 plus 1, 4 times 2 is 8, plus 1 is 9. That worked. Okay, well, what about the fifth term? 4 times 5 plus 1. 4 times 5 is 20, plus 1 is 21. And sure enough, our fifth term was 21. So that's a little trick that may help you. If you notice they're adding the same thing every time, try multiplying that number by n and then see if you can add or subtract an adjustment to make it work. Okay? Like I mentioned, sequences are functions, but we typically use n rather than x. So in my formula up here, instead of saying y equals 4x plus 1, I put n in the place of x, and I used a sub n instead of f of x or y. Okay? All right, 2 types of sequences that we want to kind of be aware of. One is called an infinite sequence, and one is called a finite sequence. Infinite means it goes on forever. This sequence right here was infinite. The ... meant it kept going forever and ever and ever. Finite sequence would have a stopping point. It may only have 5 elements. If I stopped right here at the 21, it only had 5. So infinite would have a ... to say it keeps on going. Finite only has a set amount of terms in that sequence. So number 1, they want the first 5 terms in this sequence, and then they also want us to find a sub 10. So a sub 10 would be the 10th term in the sequence. All right, so a sub 1, that means what's the value of the first term? I plug in 1 for n. So 1 squared plus 1. Well, 1 squared is 1, plus 1 more is 2. All right, a sub 2 will be 2 squared plus 1. So I'm just rewriting the formula and putting in whatever term number I'm interested in. 2 squared is 4, plus 1 makes 5. The third term will be 3 squared plus 1. 3 squared is 9, plus 1 is 10. Fourth term will be 4 squared plus 1. 4 squared is 16. 16 plus 1 is 17. Fifth term, a sub 5, will be 5 squared plus 1. So 25 plus 1 is 26. So notice if I wrote the numbers out kind of side by side, I would have 2, then 5, then 10, then 17, then 26. That's the first 5 terms in this sequence. They also wanted the 10th term. So 10 squared plus 1 would be 100, plus 1 more is 101. So notice the 10th term would be 101. Number 2, same idea. They want the first 5 terms of this particular sequence. They also want the 25th term and the 100th term. And then they ask us to make a prediction about positives or negatives. We'll talk about that in a second. All right, so the first term, a sub 1, will be negative 1 to the 1 plus 1. Every time there's an n, I'm putting in a 1. Times 5 times 1. So this 5n is 5 times 1. All right, well, that's going to be negative 1 squared, because I add up that exponent. 1 plus 1 is 2, so I've got negative 1 to the second power times 5 times 1, and 5 times 1 is 5. Well, negative 1 squared is going to be a positive 1, and then the positive 1 times 5 will be 5. A sub 2, the second term, negative 1 to the 2 plus 1, and then 5 times 2 will be multiplied by it. Okay, well, that's going to be negative 1 to the third power, and then 5 times 2 is 10, so this negative 1 to the third power will be multiplied by 10. Negative 1 to the third power means 3 little negative 1s. Well, negative 1 times negative 1 is positive 1, times another negative 1 will be negative 1, times this 10 would be negative 10. Now, as much fun as this is to do by hand, we could also just type it in our calculator. I could say negative 1 to the 1 plus 1, arrow out of that, and then 5 times 1. So notice I have typed in my calculator the whole formula, except everywhere there was an n, I put a 1. And that worked out to be 5, which is what I got by hand. If I do a sub 2, the second term, I could retype it, or watch this. I'm going to push the second button and then enter, and it's going to repaste the last thing I typed in my calculator, and then I can just arrow over and change those n's where they used to be 1s. I can change them to 2s, and I don't have to retype the whole thing, and I get negative 10. So the third power, or the third term in the sequence rather, instead of retyping the whole thing, I'm just going to change those 2s to 3s. Now, one thing I would point out here, that comes out to be 15. One thing I would point out here, notice how the negative 1 is receiving an exponent. So negative 1 was raised to whatever my term number was plus 1. 1 plus 1 is 2. When we raise a negative number to an even exponent, it's going to come out positive. 2 plus 1 was 3. So when I raise this negative 1 to the third power, an odd exponent, my answer came out negative. So notice that I'm not surprised that when I had my third term, I would have been raising the negative 1 to the 3 plus 1. So it's going to come out positive again. I bet the a sub 4 is going to come out negative. Let's see if that's what happens. Changing all my 3's in that previous typing in to 4's, and sure enough I get negative 20. I bet a sub 5 is going to be positive. Let's type that in and see. And it is. It's positive 25. So notice how it kind of alternates. Positive, negative, positive, negative, positive. I bet a sub 6 would be negative, and so on. They also wanted us to find a sub 25, so I could plug that in. I'm going to change my 5's to 25's. I got, let's see, 125, or a sub 100, changing my 25's to 100's, and we get negative 500. So notice every time we had an odd term, first, third, fifth, 25th, our answer came out positive. And every time we had an even term, the second, the fourth, the 100, our answer came out negative. So if I were to find the 37th term, well, 37 is an odd number, so I bet it would come out positive. If I wanted the 42nd term, well, 42 is even, so I bet it would come out to be a negative number. Okay, so that's kind of the pattern here. Odds are positive, and evens were negative. And we are actually going to use that to our advantage. This is what we call an alternating sequence, when the signs alternate positive, negative, okay? And the way that we do that is by creating our general term where there's a negative 1 to an exponent. If you want your odd number terms to be negative, and your even numbered terms to be positive, you would want to have a negative 1 raised to just the n power. because if I put in a 1 for my first term, negative 1 to the 1 is negative. If I put in a 3 for my third term, negative 1 to the third will be negative. So our odd number terms are negative and the evens are positive. When you put in a 2 for the second term, negative 1 squared is positive. If you want the reverse of that, which is what we had here, we had our odds were positive and our evens were negative, then you want your exponent on the negative 1 to be n plus 1, which is exactly what we had in this previous example. Okay? So when you plug in an odd number, your exponent becomes an even exponent. 1 plus 1 was 2, and negative 1 squared is positive. So notice that little trick, and we can use that to our advantage when we create our general terms. So notice what happened here. They have a negative 1 raised to that power. So here's going to be a case where the odds are going to be negative and the evens are going to be positive. They want our first 4 terms. Now notice instead of negative 1 to the n, they have a negative 1/3 to the n. But isn't that still just however many negatives you have being multiplied together? So that same idea will hold even though they used a 1/3 here instead of a 1. Okay? So our first term will be 3 times negative 1/3 to the first power. Negative 1/3 to the 1 is negative 1/3. 3 times negative 1/3 will be negative 1. Okay. We put in our 2 for our second term. 3 times negative 1/3 squared. Well, negative 1 to the second power means negative 1/3 times negative 1/3, which is positive 1/9. And 3 times 1/9 is 3/9, or positive 1/3. Our third term, 3 times negative 1/3 to the third. Well, negative 1/3 to the third, negative 1/3 times negative 1/3 is positive 1/9. Positive 1/9 times negative 1/3 is negative 1 over 27. So negative 3 over 27, which would reduce to negative 1/9. And then our fourth term, 3 times negative 1/3 to the fourth, would be 3 times a positive 1 over 81. When you multiply that by 3, 3 over 81 is 1 over 27. And certainly this may be one that you want to type in a calculator, and you absolutely could. But again, notice how those signs are alternating, negative, positive, negative, positive. And this time it's the odds that were negative and the evens that were positive because they raised the exponent to just n instead of n plus 1. Okay? Recursively, the second part here, we're not going to worry about recursively. That's not something we have to focus on, so we'll skip the rest of that page. And they want us on this next page here, page 3, to just look for a pattern, okay, and find the general term, a sub n. In other words, write a formula for a sub n, okay, where you could plug in a 1 and out would come your very first term of negative 1. If you plug in a 2, out would come a positive 4. If you plug in a 3, out would come a negative 9. Okay, well, they are doing that alternating sign business. So we're going to want to have a negative 1 to the n. And the reason it's n instead of n plus 1 is it's the odd numbers that are negative. When I plug in a 1, negative 1 to the 1 would be negative. If I plug in a 3, negative 1 to the third would be negative. So my odds are negative and my evens are positive. If I put in a 2, negative 1 squared is positive, and our second term was positive. Okay? So I know I'm going to need this part. What else do I need to get the number part? If I ignore the signs, I've got 1, 4, 9, 16, 25. I recognize those as being squareds. 1 squared is 1. 2 squared is 4. 3 squared is 9. 4 squared is 16. 5 squared is 25. So I recognize these as being, the perfect square numbers. So I bet this negative 1 to the n needs to be multiplied by n squared. 1 squared would give us the 1. 2 squared would give us the 4. 3 squared would give us the 9. Okay? If you want to check, so here's our formula. This is the value for the nth term, or the formula for finding the nth term. We call that the general term. If you want to check, plug it in. Negative 1 to the first power times 1 squared. Sure enough, that comes out to be negative 1. If I do negative 1 to the second power times 2 squared, sure enough, that's positive 4. And I could keep trying. For example, the fifth term, negative 1 to the fifth power times 5 squared. That does come out to be negative negative 25, which is what our fifth term was. So once you think you have the formula, check it. Okay. All right, next one here, a sub n, and we need a formula. When I see fractions, my thought is that my formula is going to need to have a fraction in it, and I may need one process for finding the numerator on top and another process for finding the denominator. It looks like the top number, 1, 2, 3, 4, is always just whatever term number in the sequence we are. If we want the first term, there's a 1 on top. Second term has a 2 on top. Third term has a 3 on top, and so on. The bottom number looks like it's always 1 higher. 2 is 1 more than 1. 3 is 1 more than 2. 4 is 1 more than 3. So my denominator, I'm just going to let it be n plus 1. So if I want my first term, I'd have 1 on top and 1 plus 1, which is 2 on the bottom. If I wanted my third term, I'd have a 3 on top, and 3 plus 1 is 4 on the bottom. So it seems like that's working. Number 10, ooh, this is a strange pattern. I've got 3, 3 over 2, 1, 3 over 4, 3 over 5, dot, dot, dot. Okay. Well, you know what? Let's think for a second here. Looks like the top number, again, we've got a fraction, so I'm pretty sure I'm going to have a fraction. And it looks like the top number is always 3. And it looks like the bottom number, I've got a 2 and a 4 and a 5, but we skipped a couple. I bet you that the first number was really 3 over 1, but they knew 3 over 1 simplified to just 3. And I bet this middle number here, the 1, was really 3 over 3, but they knew 3 over 3 simplified to just 1. So I bet they are making that denominator just n. So 3 over 1 was 3. 3 over 2 was our second term. 3 over 3 reduces to 1, which was our third term. Then 3 over 4, 3 over 5, 3 over 6, and so on. Now, these are kind of tricky. You're just kind of using some guess and check, trying things out until you figure out what this pattern is. Okay. As we learn more about sequences, if we did 8.1 and 8.2, we would learn some clearer strategies. But right now, we're just trying different things until we figure out kind of a formula for the general term. So you're just looking at pattern, using kind of some problem-solving skills to find the pattern for these sequences. Okay, something else that can happen with sequences is we can find the sum or add up the terms in the sequence. All right, so let's say our sequence was 1, 3, 5, 7, blah, blah, blah. Okay, well, if we add up the first 4 terms, 1 plus 3 plus 5 plus 7, we would get 16. The first 4 terms in that sequence add up to be 16. It comes up in math often enough where we need to add up terms in a sequence that we kind of give it its own notation and its own words and its own symbols, okay? We call this, when you add up the terms in a sequence, we call that a summation or a series, okay? And it means you're adding up the terms in a sequence. In this particular case, we added up the first 4 terms. So a shorthand way of saying, hey, add up the first 4 terms, the first 8 terms, the first however many terms, is to use this symbol right here. This is called the Greek letter sigma. Specifically, it's a capital sigma. There's also a lowercase sigma. When we see this capital letter sigma in math, we know that it means summation, to add them up. Okay. In fact, in Excel, if you have very much experience with Excel, if you see this button on an Excel spreadsheet and you click it, it means add up all the numbers. So, Excel even got in on the math notation there. Okay. All right. Below the sigma, you will put the first number in the sequence you want. So if you want to start with term number 1, you put a 1 below it. However far you want to add up, you put that number above it. We wanted the first 4 terms, so they put a 1 below and a 4 above. That means start with the first term, end with the fourth. They also wrote a little I here. This is called our index number. Okay? You can pick whatever variable you want to be your index. I used I right here. Sometimes people use N or K or P. X is a common one. In fact, in a minute on the calculator, I'll show you how to do it, and we'll use X, okay? But you can pick whatever variable you want for your index number. Your Homework Connect Math tends to use I a lot, so that's why I put I. Just be careful, that is not to be confused with the imaginary number I, okay? I just picked I for index, but that's not, the imaginary number I. Okay, what follows it to the right of the sigma variable, or sigma letter, however you want to call that, the Greek letter sigma, is going to be your general term. So they are saying the general term of this sequence, 1, 3, 5, 7, is 2I minus 1. Let's see if you agree with that. To get from one term to the next, from 1 to 3, they add 2. To get from 3 to 5, they add 2. To get from 5 to 7, they add 2. And I mentioned a while ago that if you notice they're adding the same thing every time, put that in front of your n. And then test it. Say, okay, well, if I put in a 1, 2 times 1 is 2, but I'm supposed to only have 1. My second term, 2 times 2 is 4, but it's only supposed to be 3. My third term, 2 times 3 is 6, but it's only supposed to be 5. Notice it's always off by 1. It's always 1 too high. So I bet you 2n minus 1 would work. 2 times 1 is 2, minus 1 is 1. Yep, that worked. 2 times 2 is 4, minus 1 is 3. Yep, second term was 3. 2 times 3 is 6, minus 1 is 5. Yep, third term was 5. So notice 2n minus 1 is my general term. So I put that to the right of the sigma. Now, I used an I here instead of n. A while ago, when we were practicing finding our nth term, we always wrote a sub n, and we used the variable n. The reason they put an I here instead of an n is because they picked I for the index. So whatever variable you pick for your index below the sigma, you have to use that same variable in writing your general term. So if I wanted to stick with 2n minus 1 for my general term, then my sigma would have had n equals 1 to 4 instead of I equals 1. But this and this mean the same. It's just a matter of which variable you want to use. Okay? All right, so that's what this bottom page is referencing. Whatever variable you pick, I is your index number. You always count by 1. So you start with the bottom number and go until you get to the top. Okay? And again, you can pick some other variable, k, j, n, x, whatever. Your homework program commonly uses I, so that's why I picked that. Okay, a finite series means add up the first however many terms. This previous example, this was a finite series. Remember, series is just another way of saying add up the numbers, summation or a series. And we did the first 4 terms, so this was a finite series. We added up the first 4. It doesn't have to be 4. It could be add up the first 10 or the first 20 or the first 100 or whatever. Infinite means you go forever. You don't just stop at the 10th or 20th. You literally go forever, which seems kind of strange, but there are some applications of that. When you do that, then above the sigma, usually you'd put an infinity sign to say, hey, we're going to go forever. You're never going to stop adding terms in this series. Okay, so they've asked us to evaluate these, to work them out. Okay, so the general term is just k. Notice that they used k as our index value, and they're saying, hey, start with the first term and go until the 6th. So if I put in a 1 for k, I would just have the number 1. If I put in a 2 for k, I'd have the number 2. If I put in the 3 for k, I'd have 3, 4, 5, and 6. I'm stopping at 6 because the top number above my sigma was 6. So they're telling me to start at the first and end with the 6th and add up those 6 terms. Okay, and we can add those up. So 1 plus 2 plus 3 plus 4 plus 5 plus 6, and we get 21. So the sum of the first 6 values in this sequence is 21. Now notice that this particular sequence was just the, positive whole numbers, 1, 2, 3, 4, 5, 6. So they could have just said, add up the first 6 numbers, and we would have got 21. But this is a fancier way of writing that. Okay, next example. Notice this time they want us to start with the number 3. Again, they've chosen k for the index. So they say k equals 3 up to 5, and then our general term is k squared. So we'll plug in a 3, and we would get 3 squared. When we plug in the 4, we would have 4 squared. When we plug in the 5, we would have 5 squared. And we stop at 5 because they just told us to go from 3 to 5. And we'll add those up. Okay, well 3 squared is 9, 4 squared is 16, 5 squared is 25. So I'm adding up the 9, the 16, and the 25 to get 50. Okay. Next example here, again, they're using K as their index. Did not have to be K, could have been X or P or Q or whatever, doesn't matter. The first number they want us to plug in is 1. So we'll write our general term. Everywhere we see a K, we'll put a 1. So 1 over 1 plus 1. Then we plug in a 2. So 2 over 2 plus 1. Then we plug in a 3. 3 over 3 plus 1. And so on until we get to our last term. Now, what is our last term? How high are they telling us to go? They just put an N. We don't know what N is. We don't know if it's 7, if it's 25, if it's 100. So I'm just going to say, hey, add these up. You can put, 4 over 4 plus 1. And I'm going to put dot, dot, dot to say, hey, keep on going until you get to the last one. And the last one will be N over N plus 1. I don't know what N is. N might be 7, N might be 43. We don't know. But if they suddenly told you, oh yeah, N was 25, could you keep this going until you got to the 25th one? Yes. But we have expressed that we understand what's happening. Now we could do a little better than leaving these denominators as 1 plus whatever. This first one, 1 plus 1 is 2. The second one, 2 plus 1 is 3. The third one, 3 plus 1 is 4. So notice that my denominator is always growing by 1. So notice my denominator is always 1 higher than whatever was on top. 1/2 plus 2/3 plus 3/4 plus 4/5, and so on. Okay? All right, next one. This general term is a little fancier. 4 to the I power minus 1. Notice they have switched from using K as the index variable or the general term variable to I, but they used I as the index. They used I in their general term. That's fine. You've got to be consistent with it. Okay? So I'm plugging in a 1, so I'll have 4 to the 1 minus 1. Then I plug in a 2. I'll have 4 to the second minus 1. And then the last one I plug in is a 3. 4 to the third minus 1. And I stopped at 3 because that was the upper limit there of my index number, the upper bound. We'll add those together. 4 to the 1 is 4. 4 minus 1 is 3. So my first term would be 3. 4 squared is 16. 16 minus 1 is 15. So my second number would be 15. 4 to the third is 4 times 4 is 16. 16 times 4 is 64. So 64 minus 1 is 63. So I'm really adding up the numbers 3 plus 15 plus 63, which comes out to be 81. So the sum of the first 3 terms in this sequence is 81. Number 15, notice this one's going to be alternating. It's going to be alternating between negatives and positives. How do I know that? Because they've got that -1 to the I. Okay? So my first term is -1 to the 1 times 3 to the 1. I'm replacing the i's with 1. Plus -1 to the second times 3 to the second. Plus -1 to the third times 3 to the third. Plus -1 to the fourth times 3 to the fourth. So again, I'm just writing the general term, but I plugged in a 1, then a 2, then a 3, then a 4. I work each term out and then add them up. -1 to the 1 is going to be negative, times 3 will be -3. Okay. 3 squared is 9. -1 squared in front of it will be positive, so the second term will be a positive 9. 3 to the third is 27. -1 to the third is negative, so this term will be a -27. 3 to the fourth is 81. -1 to the fourth will be +1, so that fourth term is going to be a positive 81. And then I just add them up. So -3 plus 9 plus -27 plus 81, and we get 60. So the sum of the first 4 terms in that would be 60. Okay? We can work these out individually. Let me show you a little trick. If you have a TI-84, there is a way that you can type these sequences in your calculator and it will give you the answer. There is a way to do it with TI-83s, but it is very messy and it's almost more time consuming than it's worth. If you want to come to our Zoom session, I can show you how to do that with a TI-83, but I'm never going to give you really big numbers, so I don't know that it's really worth that, but I can show you how. Remember in the math menu, we arrowed down in our last unit to log base. Right above log base was summation, and it's got that little sigma. So in the math menu, if you'll pick summation, it pops up this general format and you can fill in the blanks. So you get to pick your index variable. I use x. I just use x as my index variable. So they're telling me to go start at 1, x equals 1. I'm going to arrow up and fill in the top number above my sigma, which was 6. And then in the parentheses, you put your general term. Make sure that since we picked x for our variable here, that I need to pick x for my variable, my general term. So I just did x, and sure enough, that worked out to be 21. Let's try one of these maybe towards the bottom. So if I go to math, this is number 14. If I choose math and then go to the summation, again, I'm using x as my index number. They told me to start at 1 and end at 3. And then my general term in the parentheses here would be 4 to the x. I'm using x because that's my index variable. I know my paper says I, but I chose to type x in my calculator, so I've got to stick with it. 4 to the x minus 1. And then, sure enough, that works out to be 81, which is what I got when I did it by hand. So you can do this with your calculator if you have a TI-84. The 83s don't work. You can come see me on the Zoom, and I can show you how to do it in the 83, but you know, for no more than we needed, I don't think it's that big of a deal. All right, number 16. It's a summation from 1 to 4, but notice they're using n as the index, and there's no n in the general term. So when I plug in a 1, there's nowhere to plug it, so my first term is just the number 10. When I plug in a 2, there's nowhere to put it, so it's just the number 10 again. When I put in a 3, there's nowhere to put it, so my third term is 10. When I want to put in the 4, there's nowhere to put it, so my fourth term is 10. And then I add them up, and I end up with 40. And if you type that one in your calculator, you would get the same thing. Okay, the last group here, they just want us to write these in the summation or the sigma notation. What we just did was the sigma notation. Okay, so I'm going to have something with a sigma in it. I need to pick a variable. I'm going to use n, but you could use x, you could use I, you could use p. It doesn't really matter. I'm going to start with my first term, and I can see that there are 5 terms in this little sequence that they've written here. So I'm going to stop it at 5, and now I just need to put my general term here. I notice it's a fraction, so I'm going to consider my numerator and denominator separately. I notice that the denominators were always 5. And on the top, well, I kind of recognize this 2, 4, 8, 16. It looks like they're multiplying by 2. 2 times 2 is 4, 4 times 2 is 8, 8 times 2 is 16. And I know my powers of 2 well enough that they are just raising it, my 2, to the nth power. I know that 2 to the first power is 2. I know 2 to the second power is 4. 2 to the third power is 8. So I notice that whatever my term number is, 2 to that number would give me the numerator. Okay. If you wanted to check, you could type this in your calculator, and then you could type in your calculator 2 fifths plus 4 fifths plus 8 fifths plus 16 fifths plus 35 fifths, and they would come out the same. So these would check out. Okay, next one here. Again, there are 5 terms, so I know I'm going to start at 1 and end at the 5th. I'm going to use a different variable this time. How about I use x just to mix it up? So since I used x for my index, I need x in my general term. Okay. Let's see. Again, I kind of recognize these as powers of 2. 2 to the first power is 2. 2 to the second power is 4. 2 to the third power is 8, and so on. What about 2 to the 0? Hopefully you remember that anything to the 0 power is 1. And a negative exponent would be just stick it on the bottom. So 2 to the negative 1 would be 1/2. So what they've done here, this pattern, is powers of 2, but they started at negative 1. So what I'm going to do is I'm going to say this is 2 to the x minus 2 power. In other words, when I put in a 1, I'll have 2 to the 1 minus 2. Well, that's 2 to the negative 1, and 2 to the negative 1 is 1/2. My second term will be 2 to the 2 minus 2. That's 2 to the 0. 2 to the 0 is 1. So that one's a tricky one, but that is the sequence that they're using there. Okay. Next group here, summation. Let's use a different variable. How about we use I this time for our index number? Again, doesn't matter. You just got to be consistent. Whatever variable you use for your index, you've got to use in your general term. They've got 4 of them, so I'm going to go from 1 to 4. And I need a pattern. I notice that it's doing that alternating business again, from positive to negative. And I notice that it's my odd numbers that are the negatives. So I'm going to say -1 to the I, okay, because I want my first one to be negative and my second one to be positive. And what you may notice eventually here is that these are just multiplying 2/3 times itself over and over. For instance, 2/3 times 2/3 is 4/9. 4/9 times 2/3 would give us 8/27. So they just keep multiplying by 2/3 over and over and over. So I'm going to have 2/3 to the n power as well. 2/3 to the 1 is just 2/3. 2/3 to the second would be the 4/9. Okay, and again, you can type this in your calculator, and then you can type up the sum of these 4 items and make sure it comes out the same. Okay, number 20. Now notice this one has a dot, 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 and then it shows a last term. But the exponent on that last term looks like it's a 9. So I betcha they are going from the first term to the 9th term. Okay, seeing that exponent right there makes me recognize that it's a 9. And in fact, this is my general term. See how it's alternating signs? So that's why they've got the -1. 9 plus 1, they must have plugged in 9 for I, so I bet it's I plus 1 on the exponent there. If I put in a 1, 1 plus 1 is 2, -1 squared would be a positive, so that seems to be working correct with the alternating. And then the 2/3 to the I, because when we get to the last term, 9 would be the last thing they plugged in. So notice they gave us the general term at the very end. And then the last one, I'm going to use X for my index number. You could pick, whatever you want. Doesn't really matter. And looks like since we have a fraction, they always have an E on the bottom, but that E is raised to a power. So I'm going to say E to the X, because when I put in a 1, I would have E to the first on the bottom. When I put in a 2, I'd have E to the second on the bottom, E to the third, and so on. And my top number seems to always be, let's see, it started at 1, and then it went to 2 and 3 and so on. So I bet it's just that same number. So X would be on the top as well. But notice how far did they go? We don't know when they stopped. They have an N. We don't know if that N is the 5th term or the 8th term or the 20th term, but they went to the nth term. So notice I used X for my index, so X is in my general term, but I have to go to the nth term in that sequence. All right, and hopefully that will get you going with 8.1, our very last lesson of the course.